All right, let's dive right in. Today, we're putting on our detective hats because there's a really fascinating mystery playing out on the coral reefs of Hawaii. It's a true genetic detective story.
So take a look at this. This is a scene from Kaneohe Bay during a big heat wave. Scientists started noticing this pattern all over the place. You've got two corals literally side by side, dealing with the exact same hot water, but one of them turns completely white. It bleaches out, while its next-door neighbor looks totally fine, healthy, and colorful.
And this, right here, is the central question. It's the whole reason we're here today. With everything else being equal, the same water, the same sun, the same heat, why does one thrive while the other just gives up? And trust me, this isn't just a fluke. It's a massive puzzle for scientists, a real coral conundrum that they are racing to figure out. Let's set the scene. The year is 2015. A really bad marine heat wave is hitting the Hawaiian reefs hard. And this event, as terrible as it was, basically turned the entire bay into a giant natural laboratory, showing researchers this bizarre pattern of life and death over and over again.
Now, in any good mystery, you have to know your suspects. So, to solve this one, we need to get to know the key players, the corals from the Porades family. Out on the reef, you'll pretty much see two main shapes. You've got this mounding, kind of boulder-like coral on the left, that's Porades lobata, and then on the right, you have this more delicate, branching one called Porades compressa. I mean, they look like totally different species, right? But here's the twist. Genetically, they are unbelievably similar.
And this brings us to a really cool concept called a species complex. Think of it like a big, messy family, where it's super hard to tell where one cousin ends and another begins just by looking at them. This is a huge clue for us, because it tells us we can't judge these corals by their cover. The answer has to be hidden somewhere much deeper, down in their DNA.
So that's exactly where the scientists went. They basically became DNA detectives, launching this full-scale genetic investigation to try and crack the code of coral survival. So here's the game plan they followed. First, they went out and grabbed samples from both the sick, bleached corals and the healthy ones. Then, they extracted all the genetic data, and I mean everything, not just the coral's DNA, but its algae and bacteria buddies too. From there, they sequenced millions of tiny genetic markers and finally compared all the codes, basically hunting for that one genetic smoking gun that could explain why some corals were tougher than others. Now, the team went in with a really clear idea. They thought, okay, there's gotta be a specific gene for heat resistance, right? But what they found, well, it was a major plot twist nobody saw coming. After all that incredible high-tech work, the hunt for that simple bleaching resistance gene came up almost totally empty. There was no obvious genetic culprit, nothing that clearly separated the survivors from the ones that bleached. And this visual shows you exactly what I mean. It's called a Manhattan plot. The higher the dot, the stronger the genetic connection. So look at the top chart. That's the genetics behind the coral's shape. Look at all those skyscrapers, a huge, clear genetic signal. Now, look at the bottom chart for bleaching. See anything? It's flat, almost completely flat. In fact, it's pretty staggering. While they found hundreds of genetic markers that were strongly connected to whether a coral was branchy or bumpy, they only found a measly 10, just 10, that had even a weak link to whether it bleached. It really looked like the case had gone cold. But you know, just when it seems like a total dead end, the data often shows you something completely unexpected. And a new clue emerged that changed everything. This family tree is where things get really interesting. When the scientists mapped out the coral's genetics, they found these hidden family groups, or clades. You can see them here in blue, green, and yellow. And here's the kicker. These genetic families had absolutely nothing to do with what the coral looked like, or even whether it bleached. You could have a branching coral that was genetically closer to a mounding one than to another branching one. So the big question became, if it's not shape, then what is driving these hidden genetic groups? And the answer, it turns out, was in what the genes actually do. The strongest signals separating these families were all linked to how the corals process phosphorus, which is a key nutrient. And since phosphorus levels are really different near the shore versus further out, it suggests these corals are super finely tuned to their specific address on the reef. This totally unexpected discovery just completely flipped the script. It reframed the whole story and led to a really powerful takeaway about coral resilience, and maybe even a little bit of hope. This table really sums up the entire detective story for us. You've got these ancient, long-term pressures, like where a coral lives and what shape it is, and those have left a massive, deep footprint on the coral's genes. But this recent, intense heat stress, it's a brand new threat, and evolutionarily speaking, it's barely left a mark.
And all of this led the scientists to a really profound conclusion. They wrote that because of all this hidden genetic diversity, the capacity of these corals to adapt may be underappreciated. In other words, the raw materials for survival, for evolution, might already be there, just hiding below the surface.
Which leaves us with this final, really hopeful question. Maybe the answer to saving corals isn't about finding one single super gene. Maybe the real secret to their survival is this incredible hidden library of genetic tricks they've developed over millions of years, of just adapting to their own little corner of the world. Could that be their key to making it in a rapidly changing ocean?